Okay, in this video lesson, what we're going to do is talk about the relative strength of acids and bases, okay? And first thing we want to do with that is to kind of acknowledge the fact that what do we mean by strength, okay? Now, strength doesn't necessarily mean low pH. Strength does not necessarily mean high concentration, all right? Strength actually takes on a little bit different meaning when we talk about acids and bases. So the strength of an acid or base is relative to how many hydrogen ions for an acid or how many hydroxide ions for a base they generate. So if I put a mole's worth of acid into solution, what percentage of that acid generates hydrogen ions? Or if I put a mole's worth of base into solution, what percentage of that base generates hydroxide ions? Okay? And the reason why we identify this is because when we have what we consider strong acids and bases, they're going to completely ionize in water, which means, for example, like our hydrochloric acid here, it's considered a strong acid. When hydrochloric acid dissolves into water, it almost 100%, for our purposes we can say 100%, breaks apart into hydrogen ions and chlorine ions, okay? None of it forms in equilibrium staying HCl, okay? If you recall previous units where we talked about weak electrolytes and how when they dissolve in water, not all of those ions split apart. That's what we're talking about again here, but now we're just applying it to acid-base chemistry. So really, we're taking something that we already know and applying it to the acid-base chemistry side of stuff. Now, within our world, there are very few strong acids and strong bases. Okay, there's all kinds of acids and bases out there. But this table right here kind of summarizes what most people would consider the strongest acids and the strongest bases. And we give them the designate of strong because it doesn't just mean like, hey, they're tough. It just means that these are the ones that completely ionize, okay? So hydrochloric acid, hydrobromic acid, hydroiodic acid, chloric, nitric, and sulfuric. Now, one note for sulfuric acid, see little A here. Sulfuric acid it's actually diprotic, meaning it has two hydrogens to give. So for sulfuric acid, only the first hydrogen is the strong one, okay? Seems kind of weird. But when it ionizes, it actually ionizes in two steps. So it can give up one hydrogen ion very, very easily, okay? That is considered a strong acidic property for sulfuric acid. The second hydrogen ion, okay, does not always release. So to remove the second one would be considered a weak scenario, and we'll talk about that here in a second. Your bases are all of your alkali metals, lithium, sodium, potassium, rubidium, cesium, with hydroxide, okay? And most of your alkaline earth metals with hydroxides, okay? So it's pretty easy to identify your strong bases because they're going to have hydroxide on them for sure, and they come from the alkali metals and the alkaline earth metals for the most part, okay? There's a few exceptions, like beryllium hydroxide isn't considered strong, but I won't test you on those little exceptions, okay? It's good that you recognize these. So if we start talking about potassium hydroxide, you're like, oh, that's a strong base. I know it's going to completely ionize. Or if I talk about hydrochloric acid, you're like, oh, that's a strong acid. It was going to completely ionize, okay? In fact, if we take a look at these from the idea of their ionization, and we take a look at this table that we can add in here, notice how sulfuric acid, hydrochloric acid, nitric, the hydronium ion, all of these things when you start talking about equilibrium constants. Now this is Ka, so it's kind of like Keq, but it's a constant for acids, okay? Just as an example here, notice how it doesn't even identify a number, it just says large. Because these numbers are so big, it is so product favored, it's so much greater than 1, which we know means product favored, that we can assume all of these are completely ionized in solution, okay? One thing to note is hydrofluoric acid right here, HF. Okay, so maybe on your notes over here, make a little note or something, put a little star saying not hydrofluoric acid for strong. Okay, and the reason why we note that is because hydroiodic, hydrobromic, hydrochloric, all of your halogen based acids are strong except for hydrofluoric acid. Okay, and the reason why, well, fluorine is so electronegative, is that fluorine likes to hold on to its hydrogen ions better. So it doesn't let those hydrogen ions separate in water as well. Water doesn't have enough strength to do its hydrogen bonding to pull that apart, okay? So it actually kind of correlates back to things that we've talked about before, where fluorine being so reactive isn't going to give up that hydrogen ion and break that bond as well. So it's going to be considered a weak acid. Even though it's a strong bond, it's still a weak acid because it doesn't completely ionize in solution. Okay. Now, if we keep this idea rolling about our acids and bases, so what's it mean to be a weak acid or weak base? Okay, this means that they have a noticeable percentage that does not ionize in solution. So if you put a mole's worth of acid in solution, you're not going to get a mole's worth of hydrogen ions. Or a mole's worth of base, you're not going to get a whole mole's worth of hydroxide ions. So per unit, they're actually providing less hydrogen ions or less hydroxide ions, which means they're weaker because the properties of acids and bases come from the amount of hydrogen ions that get generated or how much they imbalance that water equilibrium we've been talking about. Okay? Now, when they do go into solution, they do form equilibriums. Okay? And we're going to go over to this animation by FET. And this FET animation, what I like about it is it does a really good job of visualizing that. Okay? So we'll bring this thing down in and take a look at it. And what we have here is we have considered a weak acid. So strength-wise, we've clicked over to weak. It's an acid. And right now the concentration is 0.01. So we're going to turn this thing up. And notice how if I change my concentration, as I put more of them in, you see more of them forming in the magnifying glass. If I take less out, there's less in there. Okay, so we're just going to put it like right around 0.1, someplace in there. There we go, 0.1 molar. Okay, so if we look inside at the microscopic view, we have the acid here. These are all in solution. Okay, these are all dissolved. Okay, so we put the water in there. There's all kinds of water behind this, but we're going to turn that off because the water, or these molecules here, just kind of get in the way of what we're trying to look at. So we're going to turn that off and ignore the water. So in solution, when this dissolves, this weak acid dissolves, some of them stay together, these grays, they stay together. Some split apart and make the conjugate base with that hydronium ion or those hydrogen ions again. But notice there's a significant amount that don't make these hydronium ions, all right? Now, if I were to strengthen this acid, okay, now you can't strengthen an acid, but for this simulation, I can say, well, what if this acid was stronger? Watch as I slide this thing over to the number of blue and red that show up on our screen. Okay? Hopefully by now you're noticing that we're getting a lot more blue and red, and for every one blue and red we put on, we're removing one of these grays. Okay? So the stronger our acid, the more this equilibrium is going to be product favored. Okay? We're going to make more hydronium ions, make more conjugate base, and use up this, which is preferred, right? For a strong acid, you don't want HA because the HA, the hydrogen is bound to the A, and it can't act as an acid in this case. It still acts as a typical ionic compound or even a molecular compound. This is where we get the acidic properties, is by making these. Okay, so the stronger we make this, you know, at some point we can almost, if we go all the way over, we can almost eliminate, not completely, because there's a few down here still, that in our system. Okay. Another way of looking at it, instead of looking at it through the molecular view, we can look at it through concentrations. Okay, so here's your concentrations. As I slide that to be stronger, notice how the concentration goes up while those concentrations go down on there. Okay. One other view, which is useful for us, if we make this thing really weak, if we go back to our concept of electrolytes, we see that the light bulb will light up because we do have ions in solution here because it is a weak electrolyte. Notice how it's not that strong. And then as I pull the slider over and make this stronger and stronger and stronger and stronger and stronger, okay, it's making these radial lines darker yellow and longer to represent more and more electricity being flowing. So the stronger the acid, the better electrolyte it'll be because we have more ions in solution. Again, that's a review thing. We've already talked about how electrolytes work in solution. Okay. Now we can do the same thing for bases. It doesn't change anything. It's the exact same scenario, except for we're producing a conjugate base and hydroxide ions instead. Okay. So the take home here is that if you have a weak acid or base, you're not going to get 100% ionization. So if you don't get 100% ionization, we form an equilibrium. Okay. And if we form equilibriums, that means we probably want to have a way to quantify this. Okay.